Hi. All right, so 3 molecules you have, sorry. All right, so everyone just calls it COX. You have COX 1, COX 2, COX 3. COX 1 is accountable for all mucus creation. So when you have COX 1 working as an enzyme, what it does is it creates this mucus, especially like the mucus obviously that you find in your nose, the mucus in your stomach acid. COX 2 accounts for pain, so it sends a lot of those pain signals through your body, and no one really knows what COX 3 does. It's a grand mystery. So essentially what you need to think about is aspirin, or not actually aspirin itself, but the key ingredients in aspirin, salicylic acid, stop the production of this. So that's why, like, when you take aspirin, sometimes you experience stomach pain because you no longer have COX 1. And so what happens is your body's no longer secreting that mucus that is in your stomach lining, and the pH of the stomach is 2. So that's really acidic, and so that's why you'll experience some discomfort, because you're no longer secreting the mucus that creates that protective layer. It's all out. It also, however, eliminates pain, which is what we're looking for. That's the one that people take aspirin for. And then COX 3 is also out. Again, we still don't know what it does, but whatever it does ceases once you take Advil. Aspirin. So, why is this important? What does any of this have to do with declotting, right? Aside from the aspirin, which is what we were testing. Well, turns out that COX, and this is not what COX 3 does, but both COX 1 and COX 2 are confirmed to create something very, very important to thrombin. And so essentially, what happens is they create this thing called thrombose A2, which is another one of those wonderful Roman numerals in the coagulation cascade that we were talking about earlier. And it is probably one of the most important, and without it, thrombin ceases to exist. No thrombin, no fibrin, as we have discussed many times. So when you have the aspirin, going back to what we were talking about, aspirin cuts off COX, cuts off thrombin A2, cuts off thrombin, cuts off fibrin. The coagulation cascade is fascinating in the sense that it's a lot of really small steps that happen really, really fast, and if one of them is missing, you don't have your product. It will not work. You need every step to be exactly in place as it should be. And so, essentially, now that we know that that's the key role in aspirin, you have to look at what are the implications of aspirin outside the body, which is what we were testing. We were looking at blood clots that were not inside the body, because blood naturally declots. When it's inside the body, there's a whole other process that we kind of mentioned briefly after all of the coagulation cascade has formed the fibrin. It essentially sets in these plasmid kind of self-destruct things. We're not going to get into it, but when the thrombin is built, it's built to be able to decompose. And so that's something really interesting. Another really important thing is, after doing some research, we came across a study that showed thrombin can exist outside the body for a very, very long time. It's fascinating. They conducted a lot of experiments extracting thrombin through snake venom, and thrombin can live outside the body for 8 to 10 days. Totally fine. Temperature, they did a couple experiments where the temperature was controlled, a couple where it wasn't. It was fine either way. It turned out really well for them. However, fibrin, on the other hand, which they also conducted an experiment, can't live outside the body for more than 2 hours, which is interesting, right? Because that means that's entirely wrong. Sorry. Fibrin has a much shorter lifespan outside the body. It can sustain itself, but not for very long. Essentially, when thrombin creates fibrin, they're tied, right? But thrombin lasts a lot longer than fibrin. So, fibrin dies out pretty fast outside the body. Not in a matter of hours, which would explain why we were looking at was still clotted, but not nearly 8 to 10 days, which is why your body can sustain clots a lot longer within you. And again, if you have that constant thrombin coming in, that's how you get things like clogged arteries, etc., because that clot can sustain itself off your body's internal source of thrombin, and thrombin lives pretty well on its own anyway. But the thing to keep in mind when you're looking at a blood clot is the thrombin's not an active ingredient anymore. It's kind of out. The fibrin is the important part, and the fibrin's stuck there. It's no longer tied to thrombin. That bond is broken. They're not in the body. You're just looking at a mesh. And so, since aspirin just stops thrombin, and thrombin creates fibrin, but they don't really need each other after that, essentially, if we'd have reconducted our experiment and done it probably more correctly, then what you would anticipate seeing is actually being able to add salicylic acid and not see that declotting, because your fibrin already exists, doesn't need the thrombin anymore. So the fact that this aspirin is stopping this COX, which is stopping this thrombin from being produced, shouldn't matter. It's all over. It's said and done. And so, if we'd have reconducted this experiment, some things we should have considered were undoubtedly the pH of the blood, just so that, and also the pH of the salicylic acid. Just because if the salicylic acid's pH is a lot higher than the pH of the blood, then what you're seeing isn't actually anything to do with the biology of how salicylic acid interacts with fibrin. It's all about denaturing, and since fibrin's an enzyme, what you're watching is just the denaturing of fibrin, which we suspect is what we did, because the pH of salicylic acid is pretty, it's pretty acidic. It's not too bad, but as the name suggests, it is an acid, and blood, this is an estimate because we didn't actually take the pH of the blood in our experiment, but it's a pretty solid assumption that it sits at about 7, because the pH of blood is 7.4, so within a few decimal ranges outside the body, I'm sure it would probably still be there. If you'd have added the regulation amount, which was a little bit less than half of what we added, then I would be completely confident in saying that you wouldn't actually watch the blood declot, which is kind of interesting, right? So, again, reconduct this experiment and think about it more in terms of thrombin being really related to aspirin and fibrin being kind of its own entity. And think about pH, obviously. More control variables, because we did not account for enough. I would say 3 is undoubtedly not enough. I would also say that another thing to consider if you were reconducting this experiment is be very, very careful on your measurements of aspirin as well as your measurements of water. Take the molarity of your solution that you're adding to your blood. Also, I would say you should run an experiment where you let the fibrin try to sustain itself outside the body, which should kind of begin to stop working in a matter of, I'd say, probably 2 to 3 days, just so that you could verify that it's not the, it's the fibrin that you're looking at. Because if those blood clots are still there, then what that means is essentially you're not looking at the effects of the fibrin. And also, last thing that probably could have been way more concise was just record the amount of blood that you use. It's very important, and it was not accounted for in this experiment. So take all of that into consideration if you were to reconduct this experiment. And again, based on this understanding of aspirin and the isotopes of COX and those effects on thrombin, in turn effects on fibrin, all the wonderful things we've been talking about, you should be able to witness what would be no declotting. All right.